Hello, everybody. Welcome to Wednesday's Zoom for Organic Chemistry 2. And we're going to start off by looking at Chapter 16, Continued. We're going to look at the Wittig reaction over here and the Arbuzov-Horner-Wadsworth-Emmons reaction, which is a modification of the Wittig reaction. The goal in both reactions is to create, down here, alkenes. The Wittig protocol creates Z-alkenes as a major product, with the E being minor. And the Arbuzov-Horner-Wadsworth-Emmons modification flips the regioselectivity and gives us, so that would be stereoselectivity. It gives us the E as the major and the Z as the minor. We won't be going into great details about why E and Z are major and minor, but you do need to know which one creates Z as major, and that's the Wittig, and which one creates E as the major, and that's the Arbuzov-Horner-Wadsworth-Emmons. How do we start these processes? We'll always start with an alkyl halide or an equivalent. A carbon with an excellent leaving group would be an equivalent. And we react them in the Wittig. This is the setup to the Wittig. We react it with this specific molecule here, triphenylphosphine. It's a phosphorus nucleophile. Please recall that your periodic table tells you the phosphorus is right underneath the nitrogen, so that it behaves much like a amine nucleophile, and it attacks the carbon with the halogen, and it's a backside attack. We know that as an SN2 reaction. And we create what we call an Illid precursor. Yes, another organic chemistry word that we pronounce not the way we would first predict from its spelling. Illid is what this is called. No, this is the Illid. This is the precursor. It's not yet an Illid. I will discuss why not in a second. We have a new pKa here and another new pKa below, and we'll decide why this is the higher number and this is the lower number shortly. And the pKa is 30 for a Illid precursor, and it's fairly easy to take this proton off if you use a strong base like hydride, and there is an Illid. The definition of an Illid is quite simple. It's a species that has an anion on an atom adjacent to a cation. I could paraphrase that as a vicinal anion-cation pair. And that's an Illid. We're going to make an Illid equivalent down here using the Arbuzov synthesis. Arbuzov is the gentleman that gave us the chemicals that we can use in the Horner-Wadsworth-Emmons reaction. Most textbooks and literature sources, they don't give Arbuzov the credit he deserves. But without him, there is no Horner-Wadsworth-Emmons reaction. You start with a phosphorus nucleophile that's a little different. This is a triester of phosphorous acid. Phosphorous acid is H3PO3. Let's put that over here. Cross your fingers. Here we go. And that's phosphorous acid. Phosphorus. That's an O there. Acid. H3PO3. You're probably more familiar with phosphoric acid. It has H3PO4 as its formula, and remember, OUS acids have one less oxygen than ic acids. And the ion would be with O minus, O minus, O minus, PO3, 3 minus. Is phosphite as opposed to phosphate, which is PO4, 3 negative, one more oxygen. This is an ester of phosphorous acid. It's got ethyl groups in place of each of these hydrogens, and it acts like a nucleophile. So it's not typical of an ester that the group that makes it an acid is also a nucleophile, but it happens here with a lone pair, just like up here. And we will be reproducing each of these mechanisms on a practice page next. That's why I'm just looking at them here, and we'll do our own version on the next page. Starts off similarly like an SN2 reaction as in the previous one. And then these ethyl groups, they are unhindered groups that can be attacked on the back side, and that's how this thing gets neutral. Instead of stopping with a P plus like we did here, we do a backside attack. Where'd the bromide come from? Well, it got booted off right here. We ignored it up here, it just left and it was gone for the day. Here, bromide is still around and has something to do here because there's a electrophile, and this thing becomes neutral, and you get a double bond here. And this is our Arbuzov reagent. Why does it have a lower pKa than the Illid precursor? Well, if you look at the two products, this one has a resonance that can extend all the way to the O minus. If you resonate here and then break this pi, you get an O minus. And this resonance up here only goes between the C and the P, giving a fairly weak C double bond to P and no minus charge on an oxygen. Here, resonate to an O minus was probably a better resonance form, isn't it? So creating resonance makes it easier to take the proton off. That's a common theme we've seen with acid-base chemistry, isn't it? All right. You'll notice we had to use a very harsh base up here. Hydride bases have to be treated with very strict conditions with equipment that most labs like ours aren't really capable of doing, often involving inert atmospheres like argon or nitrogen instead of using a flask in the air. And down here, hydroxide can be used even though it's an unfavorable equilibrium here. Why do I say it's unfavorable? Well, 20 goes towards, yes, the product here that isn't shown is water. And the pKa of water, 16. And you know full well that equilibriums going from 20 to 16 lie predominantly to the left. This is not a problem. We do this reaction in Orgo 2 lab. We used to do it in Orgo 1 as well, but we moved that lab to Orgo 2 lab. And you can make it work even with this base that's unfavorable just by using a very large excess. Like 1,000-fold excess can push you towards the product here. And there you have your Illid equivalent and your Illid. You are set up to do your Wittig reaction with your Illid and your Horner-Wadsworth-Emmons reaction with your Illid equivalent here. In both reactions, the anionic carbon behaves like a nucleophile. No surprise, I hope. That's a principal focus this semester, using anionic carbons, isn't it? Grignards, organolithiums, acetylides, we've used them all. And they will be attacking the more positive portion of an aldehyde or a ketone. Please don't forget, we're studying chapter 16 still, which is all about aldehydes and ketones. You can do this reaction with aldehydes or ketones. I just chose benzaldehyde to start with. It's common aldehyde we use a lot. And not only is the Illid a nucleophile, but phosphorus, being in row 3, can handle a 5th bond. Yes, that's an octet violation when we're done. And one of the reasons this happened is we've got no charges. Instead of having an O minus and a P plus, they're both gone. This breaking to an O would be an O minus, and then it attacks the P. We never even see the O minus. And you get this strained intermediate. In the text, you'll see it's called a beta-ene. The alpha carbon has the O, which will, with the O here, and the beta has the amine equivalent of a phosphine. So it's a beta-ene. And there's these words here, kinetic product and thermodynamic product. I'll reserve discussion of those until shortly. And what happens with the kinetic product is it breaks apart to get rid of all this strain down here. And we make a Z-alkene major using this arrow here. That will make a double bond between the carbons. And you'll also get a pi bond between the phosphorus and the oxygen with that second arrow. Which one of those do you think leads the proceedings? Which one starts it off? Well, generally we break weaker bonds before stronger bonds. So I would suspect that a carbon phosphorus bond would be the weakest of all 4 bonds. And that probably happens first, and then that will create a cation here, which draws in these electrons. You do not need to show me on the test which one happens first. I'm just describing that for those that might be interested in it. The kinetic product is just wording that says this is the first thing that happens, and in a kinetic reaction, it's the only thing that happens. In a thermodynamic reaction, you start talking about equilibrium, which means you have a reversible process. And we will talk about this more during test 3 than test 2, where we'll really get into kinetic versus thermodynamic control of reactions. But for now, just a thermodynamic product, we hinted at the word thermodynamic the other day, is one that just says you're going to make the more stable product. And yes, an E-alkene here, a simple E is more stable than a Z. The mechanism is almost identical. These arrows were copy pasted. That's a confession. Look, they're exactly the same, aren't they? And you can't have 6 bonds to phosphorus. So you compensate by breaking the pi bond between the P and the O. And that's the only difference down there. And you get this square here with an O minus attached to the P because you had the O here. And it breaks down in a similar way. And because you made more of this than the kinetic product, you will also make more E stilbene than Z. All you have to know about kinetic versus thermodynamic right now is the Wittig makes the less stable Z, and the Horner-Wadsworth-Emmons makes the more stable E. A little discussion about lab results here. In the lab, when you make these 3 things, it's often very difficult to get them apart from each other. The purification step at the end, trust me, I've done this reaction. It often takes you to do column chromatography twice. And even then, you still have traces of triphenylphosphine oxide, which is that molecule there. It's rather sticky. It sticks to nonpolar molecules. That problem is solved with this reaction because the side product you made here is an anion. And for my Orgo 2 lab students, they know that anions are easily removed into an aqueous environment using a simple process called extraction, which is for anions and cations, they're more water soluble. And for those of you who are taking Organic 1 lab right now, you'll see that some of you tomorrow, some of it early next week, some of you early next week when we do our first extractions. Okay, not too much lab talk. The separations are easier here. That's all we need to know. So let's see if we've assimilated this mechanism here, the two mechanisms, and we'll try our own versions over here. If all goes well, I've got them ready for us. And yeah, I've got this and it's copied down here. And then I got, that's for the, this is, how do you know this is the Wittig reaction here? You zoom in here. Does the phosphorus have any oxygen on it? No, it's the Wittig reaction. So we'll be circling the Z product, won't we? There's the Wittig Illid. How do you know this is the Horner-Wadsworth-Emmons process? Well, the phosphorus has a double bond to O. So you're going to be circling the E product. We can go ahead and do that now. It says circle the major product, Z for the Wittig, and E for the Horner-Wadsworth-Emmons. And don't forget to give Arbuzov credit. We have to make his reagent after step 1 here. We'll do, oh, I circled it in the question, didn't I? Yeah. Apparently I made those circles too close to each other. I'm just going to control Z and recircle. And we got this. We like Z for Wittig. And let's put our answer in the answer section here, E for the Horner-Wadsworth-Emmons. And we are going to start off down here. Yes, we're always reviewing our reactions that make alcohols into carbons with excellent leaving groups. And this one is making a tosylate ester. Tosylate ester. You want to review that in chapter 10. Toluene sulfonate esters are made from toluene sulfonyl chloride. And don't forget, you need pyridine as a proton scavenger. And it didn't want a mechanism there. When we do start our mechanism, we need a lone pair on our phosphorus. That didn't come out very nice. That came out worse. I'm going to put it on top. There. And this was a backside attack on the carbon that has the excellent leaving group. Good old SN2 reaction. And that makes our Illid precursor. And our Illid precursor looks like this. Looks a lot like our Illid. Oh, yeah. Just make that a 3. Wild. And this has an H up here. Has 2 if you're counting. Why did I have to put that H there? Because in step 2, I'm going to use a strong base to remove that H. What's our strong base? I could just cross off the potassium above and put this. And it's anion. There's our strong base. It's called amide. Notice I didn't say amide, even though it's spelled that way. Don't want to confuse it with the functional group that has a carbonyl. And amide is the base, and it takes the H. Don't forget the pKa was 30. That's a new pKa. Put it on your pKa table, please. Where would you put it on the pKa table? I'd put it right under a terminal alkyne, which had a pKa of 35, and right above, oh, sorry, 20. No, I put it above a terminal alkyne, 25, and below 35, which was hydrogen, H2. And now we have our Illid. This is an Illid. How do you know it's an Illid? It has atoms adjacent to each other, so they're vicinal, and one's a cation and one's an anion. I need to see the lone pair on the anion. And I'm still learning my pen. and it attacks the carbonyl, and you get an O minus. Not really. The O minus attacks the phosphorus. And we get, we'll sneak it in over here. We need a square. And the square is, if, hey, let's do some stuff here. You can do this on tests. That's R, it doesn't change. We'll have R comes to a, oh, wait. No, I don't like my circle. My circle should have stopped about right there. There. Because the carbon that's outside of R is participating in this mechanism, isn't it? And it goes there, and it's bonded to a P that has 3 phenols on it. And we have new bonds here to the carbonyl carbon, and here to an oxygen. And we'll put those in black. The O is now bonded to the P. The carbonyl carbon is attached to the other carbon. And we have a 1-ethyl propyl group. Long story short, that group right there. And what's going to happen to that species? The CP bond breaks. It's drawn towards the more electronegative oxygen. Oxygen pulls those electrons, and the other one breaks. And you are home free. You've made your major Z. You've added, with the same mechanism, you also make the E. But you would have had a wedge dash combination here, but you don't need to show that. I only want one of the products. And we're going to move on. I hope we can see that whole mechanism. Shrink it a little. I don't want it too small, though, because we're going to steal almost every part of it when we do this one down here. I don't want a tosylate ester here. I want a chloride. What's the chemicals that let us, in chapter 10, convert an alcohol to an alkyl chloride? Well, the answer to that question was O double bonded to S with 2 Cl's. You could also write SOCl2, a little shorter form. And always pyridine with either the toluene sulfonyl chloride on the top of the page or the SOCl2. Need a pyridine proton scavenger. Remember that? And we've made an alkyl chloride, an excellent leaving group. We can now do the same chemistry we did on the top of the screen. Lone pair on phosphorus attacks the carbon with the excellent leaving group. Excellent leaving group does what excellent leaving groups do. It leaves. And we make our Horner-Wadsworth-Emmons Arbuzov precursor. We can circle this and call it R. It's a separate problem. We can do a new R. And we're going to go here. We've got R attached to a C, attached to a P. Lose the top screen a little bit. We've got OET here. Oh, boo. What's boo? That's boo. Boo is an acceptable short form for, you guessed it, butyl. So here's our phosphorus with a cation. And clearly we've got some work to do. There's 2 things different. Here's our R attached to a C that's a minus. We're not ready for that yet. That's step 2. And we're also not ready for a phosphorus double bonded to oxygen. I'll give you a clue down here. When you're done, you need to make, well, I guess it's going to be a product, so you need Br attached to a butyl group, Buber. And how do you get there? Well, you need a bromide ion. No, it's not a bromine, is it? You guys are so nice. You didn't jump all over me. Thank you. You know it's going to be a chlorine. And we kicked off a chloride here, didn't we? Chloride is a nucleophile. This carbon is going to be attacked, backside attack. It's like an SN2 a little bit, isn't it? But instead of just leaving, what else does this thing do? It resonates in. That's probably the driving force for why it happens. And we've made this species here, P double bond to O. It's got 2 O-boos left. It's got our bond to C that has R. And an H. What's the pKa of the H this time? Keeping in mind that it can resonate with the O. pKa this time is 20. Okay. And what's going to take that H off? Because we are almost here. We've got all the parts except for the anion on the carbon. So the H minus base needs to take that H off. Acid-base reaction to make that. And we have H minus in step 2. And it's going to grab the H, generating an anion on carbon. And we have this species here. And that is our nucleophile for our carbonyl. And we need to finish this because our segment's starting to run a little long here. There's a lone pair on there. That's why it's an anion. And we're going to attack the carbonyl carbon. What happened last time we attacked our carbonyl carbon? We attacked our carbonyl carbon with our lone pair, and the O made a bond to P. Let's do the same thing here. And this time you've already got 5 bonds to this P, so you can't have 6 bonds to P. Maximum for phosphorus is 5. Periodic table says that with its group number. You also have to resonate the pi and break it and make an O minus. And we're going to have to sneak in our intermediate. Not a problem. We're going up here. Let's do this. We got room here. We're going to make a square with our R group. Oh, it's nice. It's under the other one. And we got 2 BuO groups. We got an O minus. That's a little different. We have our 2 new red bonds, one from carbon to carbon. And let's make sure it's on the carbon. And the phosphorus. And CO. And this time we have something that looks a little like an allyl group, but it's got a triple instead of a double bond. If you're curious, that's called a Propargyl group. And I believe that's our square. Just want to make sure you know there's a carbon here. There's a carbon there. It breaks apart like this. Let's see if we can get things bigger. And we make our desired. Yeah, got arrows on my arrows here. It's getting a little nasty. Let's go with light pink. There we go. And that,
Sir,
yes,
I have a question.
yes.
We wouldn't see the in the second mechanism, we wouldn't see the acetanilide group in the first one, right?
We did
Because
the illid. We don't see an illid. Is that what you were saying?
no, you see the acetanilide group that's attached to the alcohol in the second mechanism.
I see an
The C,
alcohol attached to a CH2 attached to an OH.
and then the C3 triple bond T.
That's my new R group. It's got the
Right.
triple bond.
So
Oh,
we could,
acetylene. Yes, that. Yep.
yeah, we can't see that group in the first mechanism, right? Because it would react with the base first before that H.
Oh, I see what you're saying here. But I also see something else that might help you. What's the pKa of a terminal alkyne?
25,
Okay, and what's the pKa here?
20,
Which one reacts first?
20.
So that's problem solved. But I like what you were saying, because you should always think when you have competing acid-base reactions, which one's going to happen first. And we're okay here, because the 20 will be ahead of the 25. And we didn't introduce that strong base until we had our precursor with the 20. Right.
Right.
Did I help you? Okay.
Yeah.
All right. And that will be the end of our segment here. And we'll pick up on the other side with a pretty short segment, maybe even a 10-minute segment. And I'll see you soon. Oh, I did. I hope I did this right.